So last time we were discussing about types of data, right? So we have defined few types of data, and yeah, those were descriptions, right? We were defining mostly the kinds of data we are going to analyze in this class, right? And today we are going to deal with some of these variables and how we are measuring these variables. Okay, so there are two things I'm planning to complete in this class. One is you should know about the difference between discrete variables and continuous variables, and the another one is levels of measurement. Okay, so scales, that's normally we call either way, either levels of measurement or scales of measurement. Okay, so what these two are. So see, measurement is what is this measurement? It's nothing but a process of assigning numbers to the quantities or variables that we are going to measure. For example, height. Height is a quantity, right? So, well, we don't know exactly or ideally what is the height of a person. That depends upon the accuracy of the scale what you are using. So, all we can do is that we can try to get as good as possible the accuracy using the best scale possible. Okay, so we are putting a number for a height of a person. For example, my height is 176 centimeter. Okay, so I'm just approximating to the nearest possible integer. So it could be with fraction as well, 176.196283 centimeter. It could be that, or much more also, right? So we are simply assigning a number to that kind of variable. Variable is something which is free to vary. Okay, in this example it is height, or Gregor Mendel's famous experiments on the garden pea, right? So what are the variables there? It is, one is color, yellow or green, then form of the flower, wrinkled or round. Okay, so these are the random variable. Random means it could vary anywhere. There is no set scores. For example, height could be anything. It's absolutely random, right? We are not putting into 3 bins of height categories. Height is a variable which is random. That's why it's called random variable, right? So yeah, the process is very familiar that perhaps we are often overlook its importance. Of course, like, it's very important to know basically what this measurement is, right? And measurement could achieve a good level of measurement or a very bad level of measurement. Depends upon how good it portrays the real value of the quantity or attribute of the quantity. For example, a person is having exactly 176.778 exact, to be exact, that is the height of it. But the measurement could be something different, right? If you use a scale, normal or tape, okay, so measurement tape, it could never post 1 millimeter. It could never be able to measure that way. But if you use something better, like for example vernier calipers, okay, so it could have better resolution. Right, so you're simply increasing the the accuracy of that measurement, right? Anyway, measurement is nothing but putting some numbers to the attribute, the real attributes. Okay. There is another concept called degree of freedom. What it is? It's very important to know what this degree of freedom is. Okay. So it is the number of values in the final calculation of a statistic that are free to vary. So your statistic is, what is a statistic? It's a single measure of some attribute of sample. Anything. For example, in this group of class, I'm conducting my first session now, and the score. Okay, so the score is not the statistic. The score, I'm doing an average of that score. So average or sigma, that is a statistic. Okay, it's a thing, a measure or a quantity that is applicable to a sample. Okay, that is what a statistic is. Okay. So degree of freedom is number of values in the final calculation that are free to vary. Okay, so again, once you exemplify it, the definition becomes a lot more clearer to you. So if I say total number of family is 8, for example, in my family, total number is 8 members of my family. So if I say number of girls in a family is X and boys is Y. So what is the degree of freedom? It is 1, because if I say girls is 6, then it is able to vary, right? These are random variables, of course. X and Y are both are random variables. But if I know any of these, the value of any of these variable, the other one automatically is known because the total is known. Is that clear? If the total is known, only one is able to vary here. Okay, so that is what it is, right? If either one knows, other is automatically known, so logically only one is free to vary, right? So this way, so x equal to 8 minus y. Okay, y equal to mx plus c, that kind of equation, you know, that is linear equation. So these kind of constraints are what you call linear constraints. Okay, so that is basically you are measuring here two measurements, right? 1 and 2. 2 minus 1 is the degree of freedom most of the time. So number of measurements minus 1. Okay, so that is what this one. For example, for coin toss, you know, head and tail, right? So total is number of measurements is 2. So only one is free to vary. Now for example, D's, you know, the 6-sided D's, a small cube, right? 1, 2, 3, 4, 5, 6. So out of it there are 6 measurements, right? But if I know only one, okay, one D's, one side, if I know, can you calculate the all other 5? No, impossible. But if I know all 5, then I know, of course, whatever is missing out of 6 is only 1, right? So only 5 is free to vary in the case of D's. Is that clear? Yes. The other one is very automatic, right? You can simply calculate it from what is given here, right? So that is what for the D's, total minus 1. 6 minus 1, that is 5 is the degree of freedom, right? So in this experiment of this Grieger-Mendel, yellow, green, color, these are the, how many variables does it have?
7.
Only 2 variables, form and color. Okay, so color it is yellow or green, form could be round and wrinkled. But number of observations, what are the number of observations here? Yellow, green, round and wrinkled. So number of observation is 4. So degree of freedom is always 4 minus 1, 3. Is that clear? Very simple. So a proof, if you want to know the proof of it, this is how it is, right? This is, if you know round, wrinkled, the total I'm writing here, you know, horizontal total here, and these are the vertical total, right? So if the whole is known, degree of freedom is 3. Because you can calculate whatever is missing there, because you know the total is 556, right? And if the total is known, only 3 are supposed to vary. So if I know 315, 101, 108 is 32, I can easily calculate, because that is what it is, right? I can minus from it. In addition, if number of yellow or green is known, either of this, number of yellow is either 416 or 140 is known, then I can simply calculate from that, minus it to get the other score, right? So then the degree of freedom is 2. And in addition, of course, all these should be known, right? These are hierarchical, and only if this number of yellow, green known without knowing total, again that drops back to degree of freedom is 3, right? So in addition, if number of yellow and green is also known, then comes again degree of freedom is only 1. That means only 1 is allowed to vary here, okay? Because this is and green, right? In addition, number of yellow and green is known, it is degree of freedom is 1. So you know, these numbers, if we know as many as possible, then degree of freedom drops down. If we don't know anything, only total is known, then the degree of freedom is number of observations minus 1. Okay, so these things you don't really need to know all these kind of you know, reduction in degree of freedom if scores need to be provided. Okay, scores are provided, but at least this you should know, right? Degree of freedom is n minus 1, where n is number of observations. Okay. So variable is a quantity that may vary from object to object. Of course, that is what the variable is. Okay, so that varies from object to object. Okay, something which is being measured. Here in the previous example, variables are color or form of the flower. Okay, or it could be height, it could be time, okay, or it could be temperature. These are the variables, right? Now, what is the sample or data set? Data set and sample are synonyms, right? It's a collection of values of one or more variable. Okay, so univariate data sets have only one variable, while multivariate data sets have more than one variable. Okay, so either one variable or more than one variable. Data set is nothing but values of that variable. So for example, It could be, yeah, the one previous example I told you, the marks of this class, student name versus marks. Okay, so that entire thing if I'm putting in an Excel sheet. So that is a data set, right, in a sheet that is called a sample. So that is my sample. Okay, so if I perform some calculations based on that sample, for example, standard deviation or average or mean, median, mode, all these are statistic. Singular, statistic. So study about the statistic is what you call statistics, right? So that is what. So variables that we measure can be discrete or continuous. So these two kinds of variables work, right? Discrete variable or continuous. So in the case of discrete, it can be placed in one-to-one correspondence with integers. So the value of discrete variables are always integer. So integer versus fractions. So numbers without fraction is what you call integer. 2 is integer, 6 is integer, 2.6 is not integer, pi is not an integer, root of 2 is not integer. Is that clear? Integer is something that do not have any fraction, very simple. So discrete variable values are always integer. Okay, so if, just think about it, any kind of variable, if I ask you, is it discrete or continuous? You should think this way. Could the value ever be a fraction? So it could never be a fraction. So that's very simple as that. Okay. So if it could be a fraction, then it could be a continuous variable. But if it's not, if it's an integer, then it has to be discrete variable. Okay. So it follows a distribution pattern, what we call as Poisson distribution, that we are going to cover up in another class, right? So discrete variables follow Poisson distribution, while continuous variables follow Gaussian distribution. There are two kinds of probability distributions. In fact, many kinds, but these two are concerned with the variables. Okay? So it can be counted and non-exactly. So that is what the discrete variables are. You can count it so that it is integer. Number of days in a week, we know it is 7. Number of work days in a week in this universe, it is 5. Right? So blood types, O, A, B group. Okay, so all these are, we can count it. There is no fraction in this kind of measurements, right? So does not have to be an integer also. Average number of girls in a classroom, 17.5. That is not an integer, but again that is a discrete variable, right? We know the score, that is absolutely certain. That will not vary, right? No swaying, and it is not affected by the precision of scale of measurement. So whatever the scale you use, whatever supercomputer you use, and you are calculating the mean of a number of girls. Average and mean are same, right? If you calculate average, average is always average, certain. Okay, so it is not increasing in quantity, right? Probability of rolling an even number on a disk, 1, 2, 3, 4, 5, 6, out of which even it will be 3 or will be 3, right? So probability is, you can say in a common way, you can say 50% chances for getting an even side on a disk, and 50% chance to get an odd side on a disk, right? So this 50% chance that we normally use in our everyday life, if you want to say that in probability, it's nothing but 0.5. Probability is 0.5 because always probability is expressed between 0 and 1. Okay, so always in fractions. So if I say there is a probability of 0.9 to rain today, that means very high probability, right? 90% in our everyday language. So that is what the probability is. Okay. So probability of rolling an even number on a disk, it is 0.5. So again that is an integer, but again that is a discrete. So being an integer, or being a fraction or being an integer is not a textbook definition for differentiating continuous as well as discrete. Okay, you have to apply your logic as well. Cost of lunch, for example, here in our canteen is 40 rupees for a lunch. It could be 40 rupees 30 paise. Okay, so again that is a discrete quantity. It's not a continuously varying because in India we have 1 paise as the lowest one, right? So there is nothing lower than 1 paise. We don't normally express in cost, right? So that variables are discrete variables. Okay, is that clear? So 40.1 for example, that is not an integer, that is a fraction, but still it is a discrete variable. Fine. So So if I say more example, number of particles emitted by a radioactive source. So counts per minute. So that is a very good example of a Poisson distribution. Right? So that is a discrete variable. Because particles are emitted one after one. It could never be a fraction of the particle. Okay? So Apgar scores of an infant 60 seconds after birth. So this score is only it's named after the person who revised this score and an anesthetist. So this is about the health of an infant after the birth. So if the score is high, means the infant survival rate of infant is also high. So this score is again it is between 1 and or 0 and 10. So that is basically an example of a discrete. Another example could be what? Marks in the class. That is again a discrete one, right? But it could be having fraction as well. But the fraction could never be an infinite fraction. Okay? And IQ score, for example. Okay, IQ scores again normally IQ scores do not have any fraction. Right? So these are examples of discrete variables. Number of children in a family. There is no confusion. There is always a discrete. Right? You can never have a 0.5 boys in a family. Right? So color of a person's hair. Black, grey, red, brown. Again, you can say, well, sometimes it is a mixture of the colors. Right? So it is not a discrete, it could be a continuous as well. Now if you look in the textbook, some textbooks say color of the hair is a continuous thing. Some say it is discrete, but I always go with the discrete assumption. Given that everybody agrees upon the color. Okay, so if a person is having slightly grey color, okay? So for example mine, I have certain grey hair, so it is like slightly grey. No issue, if everybody agrees upon that, it is a discrete, quantity is discrete, it is a slightly grey. Okay, so that is what it is. Sometimes really tricky, that is what I am saying. Okay, so you should think your logic, apply your logic, is it a discrete or continuous? Okay? So, gender of the child, of course, mostly it is male or female, right? So that is discrete. So you can also say, how about transgenders, right? So, well, that could also be, if you consider the transgender as a separate gender, again there is a discrete, right? It can never be a continuous variable, right? So state of residence of Indian citizen, Punjab or in Kerala, right? State of residence where you are living right now. So that's only one place, right? So how about in union territories, right? In Chandigarh, or you can say, oh, I'm living in Haryana as well as in Punjab. Well, exceptions are always there, right? But still again that is a kind of a discrete variable in the normal sense. Okay? So setting aside this kind of exceptions. Cause of death of a newborn, again there is a discrete, one cause. And it could also have multiple causes together acting upon. But again that multiplicity, how many factors are contributed upon the cause of death of an infant, if that is not, again there is a discrete variable, it's never be a continuous variable. Okay? So all this follow the Poisson distribution. Okay, some more examples to make you very clear about it. Number of phone calls arriving in the call center per minute. So it could never be a half call, right? Or 0.17356 call. Okay, it's always 1 or 2, right? So this is, you can count it simply. Can you count or you cannot count? That is one very important definition for this discrete or continuous. Number of goals in sports involving two competing teams. In sports means it could be a softball or it could be of course soccer, right? Goal, right? Or hockey as well. There is a goal there. So number of deaths per year in a given age group. So number of death you can measure, you can count number 1, 2, 3, 4, 5. Right? Number of jumps in stock price in a given time interval. So up and down, right? Up things you can count it, right? Under an assumption of homogeneity, number of times the web server is accessed per minute. You can never access half. You have to access or do not access at all. Dead or alive like that, right? Number of mutations in a given stretch of DNA after certain amount of radiation. I could ask you this question, and if I ask you to calculate the probability, there are two ways or many ways. Binomial distribution way you can calculate the probability, or Poisson distribution formula you can apply, or you can also apply some really tricky Gaussian formula for calculating the probability. But first of all, if I give you this kind of problem, thing you should come to your mind first is it discrete or continuous? So number of mutations in a stretch of DNA is always discrete, right? So mutations, you can count it, you can say in number, this many mutations, so this many SNPs in a gene. Where mutation can never be half mutation means no sense at all. So it is a Poisson distribution, so you will have to apply that Poisson distribution formula to solve the probability of whatever the example which I am giving you. Okay, so that is very important. Now, what is this continuous variable? The value can infinitely vary. So it's very important, it is infinity. So even you can express it in integer. So sometimes the value can be expressed in integer that is not continuous. For example, average or probability. Okay, so average of the class, the mark class, marks of this particular class, that is an integer, but of course that is not free to vary infinitely. Okay, so that is a Poisson or discrete, but in this case it is infinitely it could be able to vary, right? Examples are height or weight. Always height and weight are continuous variable. Okay, so these two are very important, very easy. Or temperature again, that is also continuous, right? The graph of any kind of melting curve of water, for example. Right? So these are continuous, infinite number of times, right? The value can be different. The height is frequently recorded only the nearest whole inch or the centimeter, right? I explained to you before as well, right? So it could be, yeah. So we are approximating the real score, that the real values of the attributes can vary infinitely. So we are simply approximating it. So you cannot say 1.76.1, that is a discrete value. 176.2 is another discrete value. 3 is another discrete. So it is all discrete. That is wrong. So we are simply approximating because of the limitations in our way of measuring it, right? So that is what. So in this case, the vernier, the principle, it's very simple. For example, if I measure here, so you look at these two lines sync each other or comes in line. Here it is, second line is coming in line with the bottom line. Okay. So in this case, it is fifth line is coming in line with the bottom one. So in this case, it is 5.5 millimeter. 5.5 millimeter means what? 0.55 centimeter, right? So the accuracy is higher. So, well, vernier, these are normal vernier calipers, and if you can use certain electronic calipers with very high accuracy, so integers can really vary, right? So that is what it is. Fraction could be extremely, the precision could be higher. So continuous variables can be measured or calculated, but only shown as a range of values, right? So that is what it is. It can be expressed as a function as well. So distance a car has traveled, length or distance, these are only approximations, right? A car is traveling, I say, it is 3,300 kilometers from my house, the place where I born, and here, Kerala and Punjab. So 3,300, again, it's just an approximation. It could be, if you express in meters, millimeter, I can increase infinitely the precision of my measurement, right? Height of a tree, again, I told you the height is a continuous variable. Acceleration of a car, so meter per second square, right? Whatever the acceleration is that, so it could vary very continuously, right? We are simply saying I drove today 40 km per hour. It could be 40.17637, right? So temperature is again another example of a continuous variable. Here velocity of an object in a free fall, this is a time and this is the velocity. Velocity keeps on increasing, right, as the time goes on, right? So it is 9.8 meter per second square. That is the acceleration, right? That is not the velocity. Velocity keeps on increasing, right? So that is continuously varying. It's not discrete varying. Step by step. That is not the acceleration. Right? It's very continuous or smooth, right? So can I have the attendance if you are done with the attendance? Okay, so I ask you certain questions, right? Number of channels on your TV. So can Sonu put the answer? It's discrete. Why? Yeah, two channels together you cannot watch, right? Or three channel. These are, right? You can count it, you can number it, right? You can count it. Yeah, sure, sit down please. Now, a person's age, can Iqbal Gil answer it? Discrete. Why so? Yes? For example, I'm 33 years old. 33, then point something I can put days. Then I can also put minutes, seconds, milliseconds. It's increasing, right? It's very infinite, so it is a continuous, right? Sit down. So I ask you elements on a periodic table to chain curves. Discrete, right? Can you say it loud, please? Yeah, so it is basically increasing in a step, right? So proton, of course, the proton number is down. Proton number in the atom, right? The nucleus. So as it's step always for number 1 plus 1 plus 2 plus 3. So it is discrete. So that's always a discrete variable. Now time of the day, I ask you Al-Qarani. Right? Yeah, absolutely. That is right. Continuous. Now I ask you for the day of the week to, Kunj Bihari Gupta. Discrete. Right? So. Right. So of course that's a very easy. Right. Now I ask you for population to Anuradha. Population of a species. It's continuous. Why so? No, it says population of a species. For example, population of human beings on planet Earth. Or universe, you can say, because in International Space Station we have certain number of human beings, right? So, is it a continuously varying variable or is it discrete? Yes? It's discrete, right? So, persons are always sit down. So, I cannot say that the population of India is, some fraction. People are one, you're counting 1, 2, 3, 4 like that, right? You can never have a half person, right? Babies are also one particular individual. So you cannot say, oh, a person who was virgin on the deathbed. Again, it's one individual, right? So it can never be a fraction unless you are doing some kind of quantum mechanics, right? That is what, the Schrodinger, he said a cat can be half alive and half dead. So unless this is a quantum mechanics, then it's always discrete, right? So that is what is a discrete. Number of genes in our DNA to Rafi Ball. Discrete. Right? Partial genes, could it be? So it's of course it's a discrete variable, right? Now length of a piece of a rope to Asim Majid. Oh, length is of course. You said discrete or what? What did you say?
It's number of genes. So you have already shown the answer.
Okay. Right. I got confused. Okay. Now I'm asking you how happy you feel now. Okay. I'm measuring the happiness. Okay. So I'm asking to Tawsif. Why? Yeah, well, sit down. So it is a continuous, right? Of course. And more than that, there are a lot of problems there. Happiness. Can you measure happiness? No. So that is the main problem, that is psychology a science or not a science. There are so many of these debates are going on, and if you read this kind of popular science articles, okay? So that is, of course, there is a continuous variable. Speed you are walking is continuous, right? You can change, you can express in fractions as well, right? Infinite fractions. Now, this is what you call the probability diagrams, okay? So, these are the scores, okay? So, it could be anything. The values of the standard, random variables are plotted here on the x-axis. And on the y-axis, it is a probability. So, this is how it is, right? This is continuous. The values, these are values, right? Values of the random variables are continuously able to vary in the case of continuous variables. While discrete variables, the values can vary only step by step. Is that clear? That is how the probability distribution graphs are. Okay, so short. So here these are actually the probability scores. Okay, and these are the values of the standard, the random variable. Here you can say this is sigma, right? Sigma, mu, sigma, what are these notations? For example, marks of the class. Okay, so I'm giving you a quiz in this class, and I'm plotting the total summary in this kind of probability diagram. Okay, so out of 100, most of the students score around 75%. Okay, around 75. So then the average of the marks in this class is 75. Right? So that is what this 7 mu stands for. Mu is the average. Okay, so most of the measurements of this class will vary around the standard deviation, around the mean of that, right? So most of the students are going to get very near the 75. So very near means that is what it is. So 75 is the probability to get 75 is very high, and very near 75 it could be plus. So that is what here this side is, right? Mu, that is the right side of mu is plus 75. Some students can get 78 also, right? It could be 70, 69, 70, that is the minus value of this one, okay? So most of them are going to get around 75, right? So that is 1 sigma, okay? Mu plus or minus 1 sigma. Sigma is standard deviation. So once we come to the standard deviation, you will know, right, how to calculate standard deviation. But that is what most are going to get within 1 standard deviation of mean, okay? So I think it won't make sense unless you know what standard deviation is. But most means 68% are going to get, okay, in 1 standard deviation of mean. Now the rest, out of rest 95% are going to get the values of that standard random variable within 2 sigma, 2 standard deviations of the mean. Okay, and then 99.7, almost everybody is going to get within 3 standard deviations of the mean. And still these are outliers. Okay, so outliers means some students can get 100 out of 100 who are not even within 3 standard deviations of the mean. So that could be here, that particular extremely high performance student could be right here. And this, who are these students here? Extremely low performance, 0 marks for example. That means not even in 3 standard deviations of the mean. Okay? So this is what you call 3 sigma rule or empirical rule, or 65, 95, 99.7 rule. Okay, so that we are going to cover up later, but just give you an overview of what this rule is about, right? So by looking at this probability distribution, you will know, are this a continuous or discrete? So here it is, the value is sum of the 2 days, where you are putting 2 days, and then you are putting the sum of the scores. So mostly it is 7, okay? And then it could vary also, right? So depends upon this one. Is it 1 sigma, 2 sigma, 3 sigma? So outliers here is 2 and 12. To get that probability of getting 2 as the sum of 2 D's is very low. Okay? So to get 2 means you need to get first D is 1, second D is also 1. To get that is very tough. And also to get 12 is also very tough, right? First D is you are getting 6, second D is also you are getting same 6, then only you will get 12. So probability of finding this is very low, but probability of getting 7 is very high. That is what this probability distribution comes out. Is that clear? So of course you will have to avoid certain dangers. For example, attaching unwarranted significance to certain statistic. You are putting some statistics and putting a lot of significance to that statistics. Okay? So efficacy of drugs, for example, you are averaging, and with standard deviation you are saying it's very effective. At the same time, one person is dying out of that particular drug, then of course that is not effective at all, right? So it is not that it's only statistic that matters, but you have to consider everything. Okay? So then manipulating our data in ways that can destroy the meaning. For example, in this case, see this car code, person is simply totaling time and temperature. Does it make any sense? Of course no, right? You have to apply the logic, that's very important. Adding time and temperature together makes what? No sense at all, right? Performing meaningless statistical operations on the data. Those things of course you have to avoid. Is that clear? Now let's start off this levels of measurement. Okay, so this is by a person called Stanley Stevens. Okay? So in 1946 in his paper on the theory of scales of measurement in science. That paper is available in the website, in the course website. Go and download and have a look. Okay? So according to Stanley Stevens, all measurements in science are conducted using 4 different types of scales: nominal, ordinal, interval and ratio. At least you should know the difference between nominal and the rest. Ordinal, interval and ratio, or you can say together. But nominal you should know what makes nominal set aside from the rest. Okay, so that's very important. So levels, attributes are properties that are similar to the numbers. I told you, right? For example, height, an attribute or standard variable. You are putting that attribute as close as possible by certain set of numbers. So it depends upon the accuracy of that measurement. Right? So when we assign numbers to the attribute, we can do poorly, or we can get a very high accuracy as well, very low accuracy as well. For example, I'm using a sand clock to measure the time. So accuracy of the sand clock is very low, right? We know, right? But we can also use atomic clock to measure the time frame. Okay, so a chronometer or atomic chronometer, where the accuracy is very high. So it depends upon how you are measuring certain attributes, right? The standard variables, in fact. So in such case, we achieve only a low level of measurement if the accuracy is quite low, right? So if the accuracy is very high, that means you are getting a high level of measurement. So these are in hierarchy. So nominal is very low level of measurement. Then comes ordinal, then come interval, then come ratio, then come absolute. That means absolutely certain. So for example, the height of a person is 100 centimeter. That is absolute. Whatever way you are measuring, it's absolutely 100, for example. Okay? So that case that is what, right? And then to the ratio. So if you come from below, so that means that you are losing the accuracy. In fact, okay, so you are losing the level of that measurement. So if the properties of our assigned numbers correspond properly to those assigned attributes, we achieve quite a high level of that measurement. That means accuracy is also quite high. Okay? Accuracy is not exactly this one to make you understand I'm using that term. Okay, accuracy. So you see nominal, ordinal, interval and ratio, these 4 levels of measurement. What are these? Nominal is same or different, only that. If I say my income is same as yours, or my income is different from yours, so that is only thing that you are going to measure. Is it same or different? That is what nominal is. Okay? In this case, ordinal, you know the word meaning ordinal, order, right? So ordering is same. If our incomes are different, mine is greater or less than yours, so the order matters there, right? So that means if our incomes are different, that means that same or different is also known there. Okay, so that means all ordinal measurements are nominal or so, because these are hierarchical. If you say ratio level, okay, so certain measurement achieves ratio level, that means it also achieves interval, it also achieves ordinal, it also achieves nominal. Okay, so interval means relative difference. So the difference between my income and yours might be say twice as great as difference between my income and the governor's. So the interval is also known there. Okay, so that is what it is. If you say ratio is 0 point. My brother's income is about 10 times what mine is. So 10 times. So if you put a ratio of my income and my brother's income is 1 by 10. My income is 1/10 of my brother's income, or my brother's income is 10 times my income. Okay, so you know this times means you are multiplying. Right? Then interval is the relative differences. You know the difference is plus or minus. So my income plus 4 is your income. If I say that way, it is an interval scale. Is that clear? So this is multiplication factor here. It is plus or minus, and this is only the order. order preserving function, ordinal. Right? In this simple example, 6 athletes try out a sprinter's position in a local track team. Okay, so these 6 athletes are running in fact. Okay, so their sprint 100-meter dash is measured by time, the chronometer, right? The watch. Okay, the 4 different stopwatch we are using it to measure the 100-meter. How long will it take to finish it? It's very simple. Now this is a true time. Okay, of course the true time, we don't know the true time, but for the sake of simplicity to explain it, this is the true time. Okay? So in this watch number V, it is a nominal scale. Why it is nominal? Because true time, see 10, 11, 13, 20, 13, 0. Out of this true time, only 2 times are same. What are these? Yeah, C and E, right? So this athlete number C and athlete number E scored 13. So that is the only thing, it's same. Same scores are only this. And according to this one, these are all different. 10 is 23, that is really makes no sense. 11 is 12, no. 13 is 20, okay? 20 is 19, 13 is 20. See, 20, 20 is same. So if 2 athletes have exactly same time of finishing, okay, so that time is preserved in this watch. So same or different, that is the only thing that this watch is going to show you. Is that clear? So are you getting the point? Yes? So 13, 13, here it is 20, 20. So same or different, that they have captured, that particular clock have captured. If you put it in the chart, these are athletes A, B, C, D, E, okay? So this is the time to finish the 100-meter run. Okay? So here you see that it is increasing then decreasing, and in this graph it is decreasing then increasing. All are different, right? Absolutely different. So but you see that here C and E are same. In this graph also C and E, scores of C and E are also same. So same or different is the only thing that it is capturing. So that is why it has achieved nominal level of measurement. Nominal, concerned with names. Same or different is name, right? So that is why it's nominal. Also we can call this kind of measurement as categorical. Okay? Category, you are putting 2 categories. Same category, different category. Right? So variables assessed on nominal scale are called categorical variables. For example, first names of the class. So again, that's a category. Good or bad. Again, it's another category, right? 2 bins you are putting, good bin, bad bin. Same bin, different bin. Effective, drug is effective, drug is not effective. So these are all categorical variables, right? You are putting in category. There is no, absolute numbers there. So there are only labels. For nominal category, we use label. So for example, rocks can be generally categorized as igneous, sedimentary or metamorphic. So these are already labeled, you are putting label. And now you put, okay, most of the rocks in the campus are igneous. Okay, so you are putting the label igneous to most. Most could be more, what percentage. Right? So, race is another nominal group, right? It could be Asian, it could be Hispanic, or it could be white or black. All these races can be nominal group. Category. These are categories, right? Or these are labels. Is that clear? So some valid operations are equivalence. Equivalence means same race. 2 are the same race. Or set membership. Member of a particular community, for example. Set membership. Membership in that particular set. Okay? So correlating to nominal categories are very difficult. So for example, Asian or Hispanic, who is better? So none. You can never say that, right? This kind of equating, this kind of nominal scale are really very tough, okay, or impossible. So deemed to be spurious, whatever the relationship between these categorical variables, all is spurious, and thus it is unimportant. Okay? So in this example, try to figure out how many people from Assam have first names starting with letter A. Could be fairly arbitrary, random exercise. Does it make any sense? No, right? Absolutely no sense. Or Jammu and Kashmir, having a first name with J. So that makes no sense at all. So that is the problem with this nominal category. Now see the ordinal. What is this scale here? The order is preserved. Here it is 10, 11 increased, then 13 again increased, 20 again increased, 15, 18, right? Then 13 decreased, 18, 15 decreased, then 13 to 0, 15 to 9, again order is preserved. Again you can say same or different is also preserved automatically. 15, 15 is same, 13, 13 is same, right? If you plot it, say, see, it is increasing then decreasing. After this value, right, D is decreasing, D is also decreasing. True time is black one, while yellow one is ordinal measure. Is that clear? Increasing or decreasing, that order is also very clear. Right? So, beside capturing same difference, stopwatch W has correct ordering. Okay? So, we say that stopwatch W has achieved ordinal level of measurement. Order is preserved. Rank ordering, that is simply puts the data on the ordinal scale. Okay, so you are putting the order, what you are measuring in the IQ score is only the order, relative differences. That who is better than who. Or rank of, for example, if I conduct a standard Mensa test in this class, okay, for IQ test. All I know is, I really cannot know that your real IQ level. All I know is that who is having better IQ, who is having lesser IQ. So same principle for gait test also. If you have done the gait test, right? If you get 816 score in gait, what does it say about your intelligence? What does it say about your subject knowledge? Nothing is known. Only that a student is getting 97 percentile. Another one is getting 60 percentile. Chances are high that 97 percentile would be better. Right? The order is preserved there. So all these percentile or rank based measurements. The other way, right? For the ordinal level, rank and percentile are quite good attributes. Right? So you can use this rank as well as percentile or more for ordinal measurements only. Okay? So this is now again the ordinal, right? Another ordinal here. 2, 3, 4, 5, 4, 1. See, increasing or decreasing, that both are ordinal. Here. See the difference. There is another very important difference here. It is 0 here, right? S, athlete number S took 0 time. So that means he might not have run at all. So time is 0 here. But both ordinal do not state is 0. That is a very big mistake. Is that clear? So, you see these are different persons, right? Alice, Bob, Claire, Dana and Edgar. Their cooking ability is measured by judge. One judge is measuring that 10, 9, 8.5, 8 and 5. Of course, Alice is the best cook here. Now your score minus 8, x minus 8, 2, 1.50, minus 3. The order is preserved here, right? Now I'm tripling the score. 30s, 27, 25, 24, 15. Again the order is preserved here. Now I'm cubing it, the score. 1000, 729, so 614, 512, 125. Cubing is also order preserving. So these are some of the operations that preserves the order. Clear? So minus or plus, then tripling, then cubing. Okay? So why it is tripling and cubing? Why not it is squaring or multiplying by itself? Okay? So power square. So that is why if I say, well, for cooking it doesn't matter, or for something else, for example temperature measured by a certain thermometer, could be negative as well, right? Minus 2 for example. And if I'm squaring it instead of tripling, minus 2 squared is what? 4. That is positive. See that minus, the order is changed there. That is why. And also cubing preserves it, but squaring doesn't. Okay? And doubling is also, right? Multiplied by 2. Sometimes it causes mistakes there. But of course the cubing is very important problem. Is that clear? Now the ordinal scale for A, B, C. So these are partial orders. Okay? C is lesser than A, C is lesser than B. Okay? A is lesser than B, C is lesser than D. B and A is not explicitly stated here. B and A. that is only logically we are concluding. If A is lesser than B, if C is lesser than B, A is lesser than B, that is we are inferring. It is not directly stated. So that is why these are weak ordering for A, B and C. And while these weak orders are 6 weak orders possible for set of 3 variables, and these are what? These are strict orders, right? These are totally ordered. C is lesser than A is lesser than B. The order is absolutely certain, right? So these are what you call as totally ordered. 6 total ordered possibility for a set of 3, and now these 6's are partial order. Is that clear? So total number is now 13 strict possible, weak ordering possible for a set of 3. Okay, so just to illustrate it. Now there is another one called interval. What is this interval here? See, intervals called here 21, 23, 27, 41, 27, 1. See that how did I calculate this 21 from 10? This is the formula which I put here. Y equal to 2x plus 1. 2 into 20 is 2 into 10 is 20 plus 1 is 21. 2 into 13 is 26 plus 1 27. So 2 into 0 is 0 plus 1 1. So this is a formula which I use to calculate the interval level. Okay? So that is what this is. Y equal to mx plus c, that kind of linear equation I'm using to calculate interval. Okay? So that is what interval. So interval, the real time and interval time, see it's almost same except 0. Right? It is 1 in the case of interval while 0 in the case of actual time. Look at here. Actual time is 0 and what interval clock have calculated is 1. So there is a mistake there. So interval and ratio are almost same. Okay, so that confusion is it's very common that people get confused. Is it interval or is it ratio? So that this kind of scale, many people are criticizing the Stephenson's scales of measurement or levels of measurement because of that. But this is very important. Okay, 0. The position of 0 is 1 in the case of interval, but in the case of ratio, I am going to say it's preserved. 0 becomes 0. So, relative spacing, not absolute spacing of values given by stopwatch Y, matches the relative spacing of the actual times. So, the relative spacing, for example, 23 minus 21 is 2. But here it's 1, right? So, there is an equation to correct that mistake. Okay, so there is this relative spacing is preserved in the case of interval measurement. Okay. So the intervals are in correct proportion, that you can see. Order also, correct order of course, and correct proportion as well. Proportion is also same. When numbers capture same difference, have the correct order and have the correct relative interval spacing, we say that they have achieved interval level of measurement. The clear interval level is also order preserving and it is also having the correct proportion of scores. Right? Another example is Celsius scale. Unit of measurement, you are defining 1 degree as 1/100th of the difference between freezing point and boiling point of water. So it is an interval scale. Okay? So that is what it is, right? So at the standard temperature and pressure, right? Standard pressure here is 1 atmospheric pressure. So that is how you are defining the Celsius scale or Fahrenheit scale. That is also an interval. Okay? And in another example, if I say today the temperature is around 31 degrees.